AI does not drink water. But the computers running AI create heat. And some data centers remove that heat by evaporating water. That is how a question typed into a phone can be connected to a cooling tower miles away. The surprising part is not that every answer uses the same amount of water. It does not. The real answer depends on where the computation runs, how the servers are cooled, and how the electricity is generated. In the next few minutes, we will trace three things. Where water enters the system. Why per-prompt estimates can disagree. And what changes when a data center is designed for a dry place instead of a wet one. The journey begins inside a chip. When you send a prompt, processors perform enormous numbers of electrical operations. Those operations move information through transistors, memory, and network equipment. Almost all of the electrical energy entering that equipment eventually leaves as heat. Thousands of powerful chips packed into dense racks create a continuous river of heat. AI accelerators can make that river especially concentrated. High temperatures reduce reliability and can force equipment to slow down or shut off. So a data center is also a giant heat removal system. The International Energy Agency estimates that data centers used about 415 terawatt-hours of electricity worldwide in 2024. Its base case projects roughly 945 terawatt-hours by 2030, with AI as the largest driver of growth. But electricity is only the start of the water story. Fans move cool air toward the computers. The warm air leaving the racks passes through cooling equipment. In one common design, that heat moves into a chilled water loop. A chiller transfers it again into a condenser water loop. The condenser water carries the heat to a cooling tower outside. Inside the tower, a small portion of water evaporates. Evaporation carries heat into the atmosphere. That evaporated water is consumed because it does not immediately return to the local water source. New makeup water replaces it. The system also drains some water to prevent minerals from becoming too concentrated. That drained portion is called blowdown. The important distinction is that much of the water in those pipes can circulate again and again. The losses are mainly evaporation and blowdown in an open cooling tower system. And not every data center uses this design. Some use outside air, dry coolers, closed loops, or hybrid systems. That is the first reason two data centers can have very different water footprints. A facility using very little water on site may still have an upstream water footprint. The electricity powering the servers has to come from somewhere. Some power plants withdraw water for cooling, return part of it, and consume part through evaporation. Other generation technologies use much less operational water. So researchers separate direct water from indirect water. Direct water is used at the data center itself. Indirect water is associated with producing the electricity that the data center buys. The distinction between withdrawal and consumption matters too. Withdrawal means water was taken from a river, lake, aquifer, or other source. Consumption means it was not promptly returned to the local water environment. Numbers for withdrawals and consumption should not be compared as if they measure the same thing. This is where dramatic headlines often become misleading. A single AI answer does not carry a fixed water price. The model, response length, chip efficiency, batching, and server utilization all matter. The cooling design, weather, grid mix, and even the hour of operation also matter. Training and answering prompts are also different workloads. Training can run enormous clusters for a limited period. Inference serves individual answers repeatedly after the model is deployed. Both use energy, but their timing and utilization patterns are different. Researchers can estimate a defined scenario when the assumptions are visible. That does not create a permanent law for every chatbot and Every location. Whenever you see a bottle per prompt claim, ask what model, hardware, facility, weather, grid, and time period it assumes. If those details are missing, the number is a slogan, not a universal measurement. It is tempting to say that a data center using no water on site must be better. The engineering trade-off is more complicated. Evaporating water can remove heat efficiently. In some climates, replacing evaporation with mechanical or dry cooling can require more electricity. That extra electricity may create additional emissions or upstream water use. In other locations, scarce freshwater makes evaporation a poor local choice even if it saves energy. The same number of liters can have very different consequences in two watersheds. Water consumed during a cool, wet season is not equivalent to water consumed during a drought. Drinking quality water is not equivalent to recycled wastewater. That is why good decisions consider water, energy, carbon, location, and season together. The goal is not to win one metric while quietly making another worse. The first improvement is to capture heat closer to the chip. Direct-to-chip liquid cooling sends fluid through cold plates attached to processors. Because liquid carries heat effectively, this can reduce the fan energy needed to cool a room. But liquid cooling inside the building does not by itself answer what happens to the heat outside. The facility still needs a final heat rejection system. That system can use evaporation, dry air, or a hybrid of both. Closed loops can recirculate the same cooling fluid instead of continually evaporating it. Microsoft reports that its newer data center design uses a closed loop with zero operational water evaporation for cooling. That is a useful design example, not a description of every existing facility. Other options include cool outdoor air, better temperature set points, and less unnecessary cooling. Facilities can also use recycled or non-potable water instead of drinking quality freshwater. Google reports considering air cooling or recycled water in locations with high water risk. Choosing a suitable climate and a less stressed water source can also change the impact before construction begins. There is no single cooling design that wins everywhere. The best answer depends on the place. So how should you evaluate the next claim about AI and water? Start with 5 questions. Is the number direct site water, indirect electricity-related water, or both? Does it measure withdrawal or consumption? Is the cooling water freshwater, recycled water, or another source? Where and during which season is the water used? And are the assumptions for workload, hardware, cooling, and grid actually disclosed? A facility-wide metric called water usage effectiveness measures annual site water use in liters per kilowatt-hour of IT energy. It can compare operations with similar boundaries, but it cannot reveal every local consequence. For that, you also need watershed conditions and the timing of demand. AI does not need water because it is intelligent. Its infrastructure may need water because computation becomes heat. The hidden system is the path that carries that heat away. Once you can see that path, the right question is no longer whether AI uses water. The right question is which water, where, when, and what the data center chose instead. If you want to follow the power lines and costs behind the same buildings, watch AI data centers explained next.